In this video, the brief explanation of Shubnikov Haas oscillations, quantum oscillations, has been explained in a very concise way. This has been covered under the outlines. 1. What is quantum oscillations? 2. In what type of materials quantum oscillations came? 3. Landau levels. 4. Density of states. 5. Berry phase. Most necessary. Why are they so much important? They reveal the information about Fermi surfaces, electron effective masses, and scattering mechanisms. Also, help to identify topological materials, Weyl semimetals, and Dirac fermions. Used to probe high-temperature superconductors and low-dimensional systems. Concise intro to all. What is quantum oscillations? Quantum oscillations. This is a peculiar phenomena of the fluctuation in magnetoresistivity at low temperature and high magnetic field, referred to periodic variations in a material's electronic properties. In what type of materials quantum oscillations came? These typically observed mostly in narrow band gap materials, like semimetals, topological insulators, and Dirac materials, etc. Landau levels and quantization. Landau levels, LLs, are degenerate with discrete energy levels, with the number of electrons per level directly proportional to the strength of the applied magnetic field. They dictate how electrons behave in strong magnetic fields, influencing magnetotransport properties. Landau quantization. The quantization of charged particle cyclotron orbits in homogeneous magnetic field. As a result, the charged particles can only occupy orbits with discrete, equidistant energy values, which are referred to as LLs. The cyclotron motion of electrons is quantized due to the Lorentz force. Berry phase. It is a mathematical interpretation over the integral of the geometric surfaces. When a quantum system evolves slowly, adiabatically, around a closed loop in parameter space, the wave function acquires a geometric phase called the Berry phase. Mathematically, for a given block state, gamma equals contour integral a k dk. The Berry curvature is the curl of the Berry connection. Omega equals nabla times. In topological insulators, the Berry phase is given by the integral of the Berry curvature over the Brillouin zone. Gamma equals contour integral omega k dk. This integral determines the topological invariant, such as the Chern number, where omega, k, is Berry curvature and dk represents an infinitesimal change in crystal momentum within the Brillouin zone. It plays a role similar to a magnetic field in momentum space. These are materials whose nature of electron wave function is characterized by a special quantity called topological invariant, which is a quantum number manifesting the different discrete energy levels, and hence their corresponding wave functions of a quantized electron system. It is protected by the quantization energy gap itself. This is called topological protection, manifestation of Gauss-Bonnet theorem, which is manifested by protection, lack of change of the quantum number, against defects as long as the Hamiltonian undergoes such an adiabatic change, due to doping, etc., that the band gap between the ground and higher states does not vanish. Here a football, which is showing continuous deformation, football to sphere, and sphere to football without changing their surface area and genus. This is still protected when the change is adiabatic. As more and more pressure applied on it will go into another shape, like torus, and not return to their original shape, breaks the topology, undergoes the external pressure applied in the real space. Similar to the topological materials, they undergoes protected by the time reversal symmetry, and works on the concept of magnetic field in momentum space. On applying magnetic field, the Brillouin zone to form in such a way that it protects their topological nature, and gives the quantized degenerate levels in which electrons can reside in these states, which are distinct corresponding to certain energy level, and shows the SdH oscillations. As the intensity of magnetic field increases, the Landau level's quantization increases and shows more and more enhancement in the amplitude. But after a certain value of magnetic field, the density of states not crosses the Fermi level and absence of oscillations. On the increment of magnetic field, cyclotron radius converges. As increases are decreases, meaning the electron's motion is more confined. This leads to stronger quantum effects. E sad phase and plus 1/2 omega. As B increases, Landau levels are pushed apart, leading to more pronounced energy quantization. More electrons fit into each Landau level, increasing the degeneracy equals /h. Quantum oscillations, like Shubnikov, the Haas effect, become more visible with enhanced amplitude. After a certain high magnetic field, quantum oscillations disappear. This happens because 1. Complete Landau level quantization, lowest LL occupation. At extremely high magnetic fields, electrons occupy only the lowest few Landau levels. If all electrons fall into the lowest Landau level, there are no higher energy states to transition between, so quantum oscillations stop. This is called the quantum limit. 2. Fermi energy pinning to lowest Landau level. The Fermi energy moves into a fully occupied Landau level at high field B, preventing further oscillations. The Shubnikov to Haas, SdH, oscillations require electrons to move between levels. When this stops, oscillations vanish.